Hey guys, I'm just going to do three sort of tricky chain rule problems. Um, they're going to show up in a similar fashion on a homework test on section 3.1 that you'll be taking on Monday. It's actually questions I've taken from AP Classroom if you've been in there in some of your other AP classes. AP Classroom can be difficult to use. The interface isn't so nice, but they've got really good questions. So I'm going to take them out of AP Classroom and put them in quizzes because quizzes just scores things better for me and it's easier for me to see the data. But speaking of AP Classroom, if you're still, when you first started in, I think September 8th, if you go back to that slide, I had you register for your AP course, and all of you are in there. Some of you are in the wrong class. So a couple things I want you to do, if you haven't already, go check and see if you're in the right class. Second, the deadline's coming up for changing your undecided, because that's what most of you clicked on when you first registered, that you were undecided if you were going to take the AP test in the spring. And we need to change that to a yes or a no, okay? And if we don't meet the deadline, which I believe is November 10th, you get charged an extra fee if you decide to go to a yes, and then at some point you can't even order anymore. So we're all gonna beat that deadline and we're gonna get it all taken care of. I want it taken care of, I think, by November 1st. So either right now, pause this video, go to AP Classroom, make sure you're in the right class. If not, send me an email and I'll have Ms. Telfer switch you. What I mean is if you're in period 6 on AP Classroom, but you're really in period 1, for me, you just need to shoot me an email and I will switch that. And again, some of you, hopefully I'm gonna ask you to do that before you get to this quiz. I'm actually making this on a Wednesday, you're not taking it to Monday. So I hope to mention it on Wednesday and Thursday as well. But just in case I forget, head on into AP Classroom. All right, so here we go. I'm gonna share my screen and we're gonna hop on and take a look at three sort of trickier chain rule derivatives. So the first one is y equals 2x over x plus 1 to the fourth. And again, I'm not going to have you turn this in on any sort of a Google form or anything because I'll know if you watched them on the little mini test, 10-point test questions. This will cover 3 of them and 3 of the more difficult ones. So it should ensure you get a 8, 9, or 10, I would think. All right, so this says find dy dx, the derivative, and simplify it completely. Well, we've got a function inside of a function, so this requires the chain rule. So we'll say dy dx equals, and remember when we have that f of g of x, or that function inside the function or the gum, we deal with the derivative of the outside function first and we leave the gum untouched. So the first thing we do is, you can pretend that's a u, and some people would say do dy du, which would be 4u cubed, but we're just going to say 4 times 2x over x plus 1, the gum, to the third. I just took care of that outside function's derivative without touching the guts, but then the chain rule says I have to multiply by the derivative of the guts. So I have to multiply by the derivative of a quotient. So I've got my quotient rule embedded in my chain rule. So that can get kind of tricky. And then I need to clean it up. And then I need to interpret it. So now to take the derivative of the guts, or if you want to consider this the gum or g prime of x, I do low, d high, minus high, d low. I draw a line and square below. That you're not going to see. Okay, it's going to be multiple choice and it's going to be completely simplified. So we need to go simplify this sucker. And in order to do that, we're going to first clean up in here. Okay, never FOIL that out. Okay, simplified is better when you can see all the factors. So we're going to clean up the top of the fraction. I'm going to leave the 4 untouched. 2x over x plus 1 cubed looks about as good as it gets. Again, I want to see all those individual factors, so I don't want to like cube that bottom or anything. But I do have a 2x plus 2 minus 2x. So I really have a 2 on the top when I clean that up and combine like terms, over an x plus 1 quantity squared on the bottom. Okay, so now, and I'm just going to erase this to get some more room on my paper. Now when I clean this up again, we want to see all the factors, but we want it as clean as possible. So on the top, I have the 4, and I have the 2. So I'm going to call that an 8. Okay, so I have the 4 and the 2. I'll call that an 8. I have the 2x cubed, which I think I'll write it so you can see that it's cubed on the top and cubed on the bottom. Then I have also on the bottom, again, I took care of this. I took care of this. I took care of cubing the top and cubing the bottom. I also on the bottom have that x plus 1 squared. From here, if you look and don't see it, because it's multiple choice, maybe the bottom became x plus 1 to the 5th. Be careful that you don't think it's to the 6th. They anticipate that. And then maybe the top does look like 8 times 2x cubed, but it also might look like 8 times 8, or 64 x cubed. So I think this is the best looking version of it. But again, you got to be able to work with all the different simplifications. I think this is simplified completely, but don't put it past College Board to leave it like this. Again, what they'll never do is like multiply that bottom out. We want to see the factors so that we can answer some questions about it. So it says write the equation of the tangent line. Remember, we need a point. I was given the x coordinate of the point, so I need 1 comma. Now I need to be on, don't go plug it in here because that's the derivative. I need a point on the curve, y equals. And I don't know what that graph looks like, but I know that y of 1 will be 2 times 1, or 2, over 1 plus 1, which is 2, to the 4th. So when I put in a 1 comes out of the original function. I also need y prime of 1, or sometimes notationally, which is coming up in the word problems, might look like that, the derivative of y when x is 1. So I need to go put 1 into my derivative function. So I do 64 times 1 cubed, which is just 64, over 1 plus 1, which is 2 to the 5th, or 32. So my slope is 2. My equation of the tangent line is y minus 1 is equal to the slope there times x minus 1. All right, next up, where on the graph of y is there a horizontal tangent line? Horizontal tangent lines occur when the derivative, or the slope, is 0. So I need to know when my derivative, my y prime, which is that 64x cubed over x plus 1 to the 5th, I need to know when is that 0. When does 0 equal that? Well, again, I've said in a couple videos that a fraction can only equal 0 when its numerator is 0. And 64 times x cubed can only be equal to 0 when x equals 0. So sometimes it'll say the x coordinates, so you'd say at x equals 0. Sometimes it'll say the points. Because this says where, you're safe putting at x equals 0, but if it said at what points, remember you would have to go put 0 back in to the original function. Let's go do that. When we do that, we get 0 over 1 to the 4th, we get 0. So either at x equals 0, or if it says what point, it'd be at the origin. I'm going to see a horizontal tangent line. Where in the graph does the derivative not exist? Well, that's actually leading into another chapter. You won't be asked that on your little homework test. Actually, you'll just be asked to find the derivative. I'm just expanding a little bit more because it's going to be multiple choice. So where on the graph of y does the derivative not exist? Well, let's go look at our derivative. It is right here. Basically, what values of x are not in the domain of the derivative? What can't the derivative be? Meaning, where does dy dx not exist? Well, I'm fine with every number in the world, but I know we can never divide by 0. So that at x equals -1, I know there's an issue with the derivative. Until we get later in our studies, you're not going to know exactly what that issue is usually, but for this one, because there is actually an issue with the original function at x equals -1, Remember, I know there's a vertical asymptote there, so I know I'm going to have a continuity problem, but you don't need to know that yet. Now it says sketch it using Desmos. So let's go to Desmos and take a look at what the graph of this looks like. So you might want to get used to using Desmos. It's kind of nice for verifying everything that we just did. So I'm going to switch screens again here. I feel like I have to sneeze. I think I have Desmos going, well, I started it. I think I started just a second here. There. All right. So I'm going to go, I hate when I say gonna, I'm going to go enter that original function back up there, the y equals 2x over x plus 1 quantity to the fourth on Desmos. So just y equals, I like Desmos because it also accepts you can see an asymptote pop up right there at x equals -1. I need to raise this, oops, sorry. Sorry, that's not what I wanted to do. I want to go back up here. Oh, I guess that'll work. I've got a lot of parentheses that I don't need, but it'll work. Now, this is kind of interesting. So let's see if what we said happens. First of all, horizontal tangent line we set at 0, 0. Do you see here at the origin? That's the turning point right there. That's where my tangent line, if I drew it, would be horizontal. So that's confirming answer C. Where does the derivative not exist? At -1. Actually, it looks like, because there's an asymptote there. So if I zoom out on this, you'll see that we've got an asymptote at -1. It's hard to see it with the nature of that graph, but there's a definite problem. And then we asked, what was the equation for the tangent line when x equaled 1? So I'm going to zoom back out here so we can kind of get in there and look at when x is equal to 1. Let me come squeeze right back in here. So at 1, there's a tangent line right here. And I said that, let's go back and take a look at what we said that was. Boy, I'm really color-coded here, aren't I? I'm going back right here if you can see. Let's go graph that line. Y equals, and it would be 1 plus, you may say, why is she writing it like that? Kind of used to it from Calc BC. This is called Taylor form of a line, which is the most beneficial form, actually. But all I did was add this over to the other side, so no big deal. But do you see that blue line popped up there? It is tangent to the curve at 1, 1. Interesting. Love it. All right, so stop sharing that. And let's see if I can remember how to click on everything here. Back to sharing screen, back to iPad. We'll do 2 quick ones and call it a day. So back to the iPad, and then 2 that just don't have any extensions to them, just regular problems. So the second one is, I call these kinds functions everywhere. You don't know what H is, you don't know what E is. If you did, that'd be kind of nice. Like if you knew that K was the sine function, then our first derivative would be e to the u du. And our second derivative, we'd use the product rule, and you'd have these explicit functions to use. But I have no idea what k of x is. So when it tells me to find the second derivative, that's what those 2 primes mean, is take the derivative and take it again. Watch what I will do. I'll take the first derivative. Remember, our derivative of e to a function of x is e to the function of x times its derivative. Some people say e to the u prime or e to the u du dx, but you just take that e to the kx and you plop it right back down, e to the u, but then you have to multiply by its derivative, and I don't know what it is. So I have to call that k prime of x. So that's e to the u du. That's the first derivative. The second derivative is now the derivative of a product. So I would do first function d second. And I don't know what k prime is, so its second derivative would be k double prime. That's first d second plus second d first. And again, the derivative of e to the u is e to the u times u prime. So another k prime of x. Now watch when I clean this up. I'm going to write it a little nicer. I have a k double prime of x, e to the kx. Plus, I have two of these, which we'd write k prime of x quantity squared, right? E to the k of x. Now I could factor out an e to the kx, k of x, sorry, I should be saying that with a little more carefully. And then in the parentheses, when I factor this out, I get a k double prime of x plus a k prime of x quantity squared. Now, some people find these functions everywhere ones easy because they don't actually have to know the derivative of k. Like if k was a function and you didn't know its derivative, like if that was e to the tangent x, and you're like, ooh, it's e to the u times the derivative of the tangent. I forgot what it is. It'd be secant squared, right? This is actually getting interesting because I like this problem I just made up off the top of my head here. I'm sorry, I'm going to go off on a tangent. Pardon my pun, but I'm going to take that e to the tangent x, and I'm going to find its second derivative because I think that sounds kind of fun. Actually, let's do the first derivative of e to the tangent squared x. Remember I said and let's just do the first derivative. Remember when I said that when you have those trig functions with the embedded powers to write it like that, I still would do that. Remember the derivative of e to the u is e to the u times du dx. So I have to take the derivative of tangent squared x. That's the chain rule. I have to bring the 2 out front, don't touch the gum, drop the power 1, then multiply by the derivative of tangent. And the derivative of tangent is secant squared. Notice when it's not like k of x, if you don't know the derivative of tangent, you can't just call it tangent prime. You have to, like you could with k prime. So some people like those functions everywhere. All right, so this was my e to the u, and then my du dx was 2. I'm going to put that out front because I like it. Let's just put tangent x and then secant squared x. And then just remember that products are commutable, so you can write that product in any order. So you might, if it's multiple choice, see the tangent x over here and the e to the tangent x over there, because 2 times 3 times 5 is 5 times 3 times 2, so order doesn't matter. All right, and the last one. This is the natural log of a function, which I'm going to call u. Okay, remember the derivative of the natural log of u is 1 over u times du dx. Or some people like u prime over u. So when I do the derivative of the, why did I write w again? That's not necessary to rewrite it, is it? Let's just launch right into w prime. I will do the derivative of u, which is u prime. Just ignore this natural log for a second. I'm going to do u prime, which is 1. It's the derivative of x, plus power rule, 10x, plus the derivative of e to the u is e to the u times du dx. So I like this because it's got both the natural log derivative and the e derivative. So that's my u prime right here, the derivative of the argument in the natural log. By the argument, I mean, what am I natural logging? All over, and then you just rewrite u. So if you can remember the rules, u prime over u. This would be an expression for the derivative. We're supposed to find it when x is 0. So we'd have 1 plus 10 times 0 is 0, right? Minus 3e to the 0, anything to the 0 power is 1. All over 0 plus 0 plus e to the 0, which is also 1. So negative 2. What does that negative 2 mean? It means, and I've been talking long enough, I didn't mean this video to be much more than 10 minutes, but I don't know how long it is right now. I can't see the timer. It means that if I were to graph this in Desmos and go to where x is 0, so wherever that graph hits the y-axis, the slope of the tangent line, also known as the instantaneous rate of change of w, is the slope of the tangent line at x equals 0 is -2. All right, that's it for that one. I'm going to stop the share, remind you to take care of business in AP Classroom, and also remind you to have a great weekend. See you later.